All right. Example 6 here. Okay, so just going through a handful of these examples. Get a little bit more practice at this. We're not going to have a homework assignment strictly dedicated to this section. There might be some homework questions that pop up in the next section that are these types of equations, but there really wasn't enough collectively to make an assignment. In addition, there are equations here that we will investigate further in other sections in much greater detail and using a little bit different structures, okay? For instance, when we get down to like this example here, that's a rational equation, and there's an issue at -4, there's a domain issue at -4 here, and we'll talk about that in an upcoming chapter about, you know, how do we address this, how do we solve it efficiently. You already know this one maybe from Algebra 2, how to solve. We'll talk about it again here. But what happens then when maybe there is a, like instead of x plus 4, maybe it's x squared plus 4, or maybe it's x squared plus 4x. You know, what do we do in those situations? And those types of equations will pop up in, like I said, later chapters. What I want you guys to understand with this course is a lot of it is not new to you, okay? You have like the foundation of a lot of these concepts. We are just going to take that foundation and continue to build on top of it, okay? You might know out of like a cluster of rational equations how to solve, like, I don't know, let's say 40% of it, okay? I'm going to try to teach you how to solve the other 60% of rational equations, okay? So example 6 here, rational equation, but it ultimately, because of where the variables are, turns into or becomes a linear equation, or is a linear equation. Let's get rid of those fractions. There's two ways to get rid of those fractions. What do you think the easiest way would be? Jimmy? Multiply by the LCD, okay? We could say, okay, well, if I look at the left-hand side and I want to get that to be one fraction, because maybe I want to look at this, say, if I can make the left-hand side one fraction, the right-hand side is a fraction, I got a proportion, I could cross-multiply, okay? But in doing that, I still have to deal with making that denominator on both those things on the left 30, right? Which 30 is the LCD, right? Okay? So I think, in general, instead of merging fractions and then using the cross product idea, just at the first step, multiply by the LCD. Okay. Now there will be aspects in trigonometry that we will need to be able to merge equations like this, or I guess expressions like this, but probably 90% of the time LCD is much more efficient, and people are a lot more successful by using the LCD instead of adding fractions, subtracting fractions, that kind of stuff. All right. So multiply this by 30, multiply that by 30, multiply that by 30. Okay. Now I'm just going to take this one here on the left, this first expression, and kind of talk about what I'm really doing. When I multiply by 30, I'm really multiplying by 30 over 1, correct? Okay. So when I multiply a fraction times a fraction, I'm taking that numerator times that numerator, right? And I'm taking that denominator times that denominator. And when I do that, before I even start combining things, I'm going to write it that way. Okay? Now, I use the commutative property to switch the 5 and the 1 around and make it as 5 times 1 instead of 1 times 5. But now I can think about how we multiply fractions if I've got two factors up here as a product and two factors down here as a product, that can be split back up. It's kind of undoing what we just did. But with the associative property and the commutative property at play here, now we can see that 30 over 5 can actually be recognized. And what's 30 over 5 the same as? 6. So that's where in Algebra 1 or Algebra 2, when you're taught, hey, just go ahead because 30 and 5 goes into 36 times, you cancel those out and leave you with 6. The logic of why you can do that is this stuff right here. Does that kind of make sense? And that's the college algebra that I want you to understand. Because if you understand that, it makes all the processes so much easier. And when it gets to calculus, it's going to make calculus something that you can focus on the calculus instead of having to worry about the algebra. That's usually what happens when we get to calculus class. You're hearing me all year talk about calculus because that's what this course is geared to. Okay? College algebra and trigonometry are geared towards you being successful in calculus. Okay? So when I'm in calculus, if I can concentrate on just the new calculus content instead of having to teach myself 3 years of algebra at the same time that I'm teaching myself calculus, I'm going to be setting myself up for success. Does that make sense? Okay. Those people that struggle in calc are usually the people that do not have strong algebra skills. Okay. So now I'm going to have 6 here, and I'm going to multiply that by the 2x plus 1. Okay, so that's going to give me, what, 12x plus 6? Okay. Same thing's going to happen over here in this next fraction. I was going to cancel 30 in the 6, so that's going to be 30 over 6, which is just 5. So now I'll have plus 5x minus 20. And on the right-hand side, those are going to cancel and leave you with 20. Combining like terms, so that's going to give me 17x. So this is, what, negative 14. I'm going to take that to the other side. It becomes positive 34 on the right-hand side. Okay. I don't, especially at this level, I'm not going to rewrite that as 17x minus 14 equals 20. I think that combining of like terms and moving to the other side of the equation is something we can do together at once. If you need that step, if I skip a step and you need that step, let me know. And I can go back. I can slow things down, but I think we should be all okay with that right now. And that gives me x to be 2, correct? Okay. You can check that pretty easy. Plug 2 in. So it gives me 1 up on this right here. So it's going to give me, what, negative 2, 6, so minus a third. Does 1 minus a third equal 2/3? Yep. Okay. So we should always be able to check our work. I will give you in this class pretty much everything that we do. I'll give you the ability to check it. All right. When I was in school, I always thought, whatever, I'm not going to waste my time checking my work. Because what happens in the off chance that I'm wrong? Then I got to redo all my work, right? Okay, so I'd rather not check it and not know whether I'm right or wrong, because then I don't have to do any extra stuff. But that's kind of stupid. And second, if I go through the process of checking my work, it reinforces my skills so much better than just doing the work one time. Does that make sense? Doing it using the analytical approach to solve it. Okay, this one here. What we're going to find out, and this is something that you guys talked about a little bit last year, domains and ranges. This equation right now, if I look at just the left-hand side, there's a domain issue. Okay, there's a value that I'm not allowed to have over here as a solution. Same thing on the right-hand side. Okay, now in this situation, it's only one value, but what number am I never allowed to divide by? 0. So when I find a solution here, and it's, in this case, we're not going to run into this problem, but eventually there will be situations where if I solve this and I get -4 for an answer, the equations tell me -4 cannot be an answer. Does that make sense? Okay. So when we start talking about functions, we'll talk about domains and ranges, and those domains and ranges then have an impact on solving equations, certain equations. So division by 0 is a problem. I just got to remind myself, hey, when I'm done, if any of my answers are -4 in this case, I just cross them out. They're not really solutions. Okay. So what's the LCD here? And here's something that I think is very important for us to understand. X plus 4 is an algebraic expression, right? But what does X represent? What does X always stand in for? A number. So if I add 4 to a number, what do I get? Another number, right? Okay. So when I see that thing that I highlighted, X plus 4, even though it's two things, it's a variable plus a real number, it is representative of just a real number, right? So I treat it just like a real number, okay? And that's the thing that I think people miss in algebra, or they don't recognize in algebra. Variables represent numbers. So whatever, if they represent a number, then I need to treat them like numbers. Does that make sense? Okay. So when we were working with, the previous example, and we had like 5, 6, and 3, and we tried to factor them to see what all our prime factors were so we could generate an LCD, this thing here, X plus 4, I don't know specifically what the number is, but it has to be part of my LCD because it is a factor of those denominators. Does that make sense? Okay. So X plus 4 is part of my LCD. If I look at 1, obviously that's got to be part of my LCD, but it's trivial. Okay, it doesn't change my LCD at all. And then here, X plus 4, well, that's already taken care of here. So my LCD here is this number, X plus 4, whatever that turns out to be. Does that make sense? Okay. So I'm going to multiply each one of these by X plus 4. And then we can start that process where if we go, X plus 4, because it's X plus 4 over 1. So I go X plus 4 over 1 times 3 over X plus 4. If we put those together, we get 3 times X plus 4 over 1 times X plus 4. What's going to happen with the X plus 4s? They cancel out, okay? So I'm going to venture to say that a lot of us are not going to kind of take the time to write that, but that's the logic of why we do this. Those cancel. Leaves me with 3, right? Does anything cancel in this second one? No, okay? So I'm multiplying a -7 times that quantity. So here's the thing, okay? You're going to hear me talk about first name, last name with signs, because I have this problem. Okay, I've had this problem with integrated 1 students. I've had it with algebra students. I've had it with geometry students. And when I've had those students in those grades and then they come back to college algebra, they end up carrying over the same problem. And we try to fix it, and then when we get to calculus, they have the same problem, okay? The number one error is that people are going to take that -7, okay, and they're not going to pay attention to the negative. They're going to say, oh, that negative needs to go right there. And then they're going to say, I'm going to take this 7 and multiply it by X plus 4. And when they do that, they get 7X plus 28. Does that make sense? And it should be 7X or -7X minus 28. Is that okay with everybody? And so you're going to hear me say first name, last name. Wherever you go, does your first name go with your last name? Right? Okay, so wherever I go, James goes with Faye, right? No matter where I'm at in the world. Okay? So when I take a number that is negative and I distribute it, its first name, it's negative, and its last name, it's quantity. They always need to go together. Does that make sense? So often people will put plus 28 there and throws everything off. Okay? So just be aware of that, be leery of that. So we get that. So now I'm looking at what? -7X equals 21. So X then is -3. And that's a valid answer, right? It was not allowed to be -4, but it can be -3. Is that okay? Yes. All right. Let's do this one here. Okay. Now here's where, So we worked on these rational equations, and this is what I was trying to say earlier in the period, is that there's some of this stuff is not new to you, but the degree of difficulty or the depth of knowledge for some of them might be new to you. Okay? So this one, a little bit different, there's a twist to it because of the x squared minus 4. Okay? You remember in previous questions, if we had like, let's say this number here was, let's say x ends up being 7. If x was 7, this number would be 9, right? This number would be 7, right? Or sorry, 5. And this would be 45, correct? Okay. Now, remember breaking this down to like 3 times 3. This was 5 times 1. This would have been 3 times 3 times 5. So we wrote this as 3 squared times 5, 3 squared times 5. Remember doing that? Okay. And we had to do that with all of these numbers to say, yeah, that's got to be part of my LCD. Yes, that's got to be part of my LCD. I already got that, and I've already got that 5. Does that kind of make sense? Okay. Now this one's a little bit unique because of how that one compares to these other two over here. But if it's an algebraic expression, you still have to factor it to find your LCD. Does that make sense? We talked previously, let's say that, I think one of the questions that we did earlier was like the LCD was 30, right? I don't have to use the LCD. I could have used 90. That's common. I could have made all those numbers grow to 90 in that previous example, like example 6 or something like that. Okay, but that's going to make my multiplication process more difficult because I'm multiplying bigger numbers. When you're working with variable components to your LCD, you always want to make sure it's an LCD. Okay, if I go through and I multiply this thing by x plus 2 times x minus 2 times x squared minus 4, use that entire thing as my LCD. Okay, because it just has to be a common denominator. It doesn't always have to be the least common denominator. But with variable components, if it's not the LCD, you're going to generate equations that you do not know how to solve yet. Does that make sense? And you're going to, even if you did know how to solve them, you're going to create then procedures that are going to be very difficult and very time consuming to actually generate answers from. Okay, so when you've got algebraic components down here, variable components, you're going to want to make sure you generate the LCD. So when we do this, remember these things stand in for numbers. I just have kind of a generic representation of those numbers. This thing here factors to those two numbers, x plus 2, x minus 2. So as I go through here, you see that my LCD should be x plus 2, x minus 2, and I will apply that to each one of these. Is everybody okay with that? Okay. So those cancel, so it gives me 7x minus 14. These two cancel, gives me 5x plus 10. And over here, they cancel entirely. So I get 10x minus 2. Move the 10x over with the 12x over here, so it gives me 2x. So that's a negative 4. Add that to both sides, gives me 2 over there. So x is 1. Does that kind of make sense? Okay. So would you guys agree that that 7x minus 14 plus 5x plus 10 equals 10x minus 2? Pretty easy equation to solve. Okay. Let me pause here real quick and see if we can get GeoGebra to cheat a little bit for us with, and we can do this by hand, but it's just going to be more time consuming. Let's go, if I took the 7 over x plus 2 and I multiplied it by x plus 2, x minus 2, and then x squared minus 4, and I want to copy that so I don't have to write it again. Well, there we go. 7 divided by x plus 2. Okay, so it would give me that thing right here for that term. Does it make sense? If I didn't multiply by the LCD. I just multiplied by a common denominator. And then if I've got the 5 divided by x minus 2 and multiply that thing, I better put parentheses on the other one. Multiplied by that gives me that. And we can adjust that in a minute. So let's go expand. Oh, doesn't do it. All right, so I got that then for the middle term, okay? And then 10x minus 2 divided by x squared minus 4 times that for the last term, okay? So what's going to happen if you just kind of add those first two together up there, set it equal to that third one, you ultimately end up with a cubic equation to solve. Does that make sense? You guys know how to solve cubic equations? Okay, so it creates algebra that either you don't know, you don't remember, or you don't want to go through because it's messier than what's necessary, okay? But if I can look at the LCD, figure out the LCD, instead of getting a cubic equation that I have to solve, I get a linear equation that we've been doing forever. Yes? Factor. So cubic equations are an extension of essentially quadratics in that process of solving quadratics, and we'll talk about that. And that's kind of a bulk of what this class is about. Is we'll spend probably about a month and a half on solving cubics and things like cubics. All right, let's say that I'm on a test or a quiz, maybe a multiple choice ACT, and I don't know how to solve this. I forget. Can I just have this in from the last class. Can I type in the left-hand side to some graphing tool? Okay, now you can do this on your TI-83. There's no difference in the TI-83 and what you're going to see here in Desmos. Maybe the approach to finding the intersection is different, but put this in the Y1, put this in the Y2, and the solution is where they do what? They intersect. Now, if I look at these, it looks like they might intersect multiple times in multiple places, right? Okay, and we'll investigate that here in a minute. And that's what this course is about. When we get later on in other chapters, we will talk about how there are asymptotes here that are actually forcing these things to only touch the one time. Okay, so if I look at this, I'm going to click on the graph, and I got some points that show up. So these are X and Y intercepts. Those are always going to show up on your graph. Okay, but this one here, if I zoom in right here, okay, can you start to see that initially the blue one was below the red one here? And then beyond this point, now the blue one is on top, right? So when I click there, I get that point. That's the intersection point. And what's the X value? 1, right? That's the solution we came up with, right? So here's my thought. I am much more successful in doing my work and getting answers if I know the answer before I even start the work. Does that make sense? So every test, every quiz you guys go through, if it's solving an equation, you should be able to get the answer and know what the answer should look like before you do any work at all. Okay? And I would suggest doing that. I think it provides a little sense of relief and sense of comfort if I can start doing my work and I can start foreshadowing a little bit and think, oh, yeah, this is my work so far. That's getting me to 1. I know that's going to work. I know I've done things right. And I go to the next problem and I address that, right? Even if I'm stuck and I don't know what to do, maybe knowing the answer will help me jog my memory. Or maybe I'm not sure, does this algebraic rule apply? Can I do what I'm trying to do here? If it generates 1, then absolutely it worked, right? If it doesn't generate 1, then the rule is probably invalid. You can't do it. Okay. But if I go look at the other parts of this, like it looks like these are, so there's a big gap right here where my cursor is, right? And that gap looks like it's narrowing here, right? Okay. But what's going to happen, and just because we're zoomed out right now, you might think, well, those things are they're going to cross somewhere over here. Okay, but no matter where I go, I think last class we went out to 300. Go a little bit further for you guys. Yeah. So if I zoom in now, my mouse isn't working quite right, but they eventually, as we zoom in and we get down to a finer detail, we find out that there is separation between them, right? We can go out to 100 trillion in both directions, and we should be able to zoom in, and there'll be a gap between them, okay? So take calculus, and I'll prove it to you in calculus with delta epsilon theorem, or proofs. So, we okay with that? I don't know. Come down to these bottom here. It says have students try. I want you guys to give number 5 a shot. What's the LCD on this guy? X plus 1, X minus 1. Good. Okay. X plus 1, X minus 1. And this here, I'm sorry. So we get that as our LCD. So then cancel, right? So that's going to be 1 times X plus 1. Okay. Over here, cancel, right? What's that going to leave me with? Negative X plus 1. And on the right-hand side, they cancel entirely, right? Leaving me 2. Okay, so the X's cancel, right? And I get 2 equals 2. What kind of statement is that? True. So how many solutions? Okay, so infinite solutions. Okay, so, and we'll talk in upcoming chapters of how we write this. But with curly brace, I'm going to write X such that X is an element of our real numbers. Okay, which is basically telling you that X can be anything. But can X be anything? What can X not be? 1 and negative 1, because in the original problem, there was division, right? So what we do is we write X such that X is an element of all real numbers, but X cannot equal plus or negative 1. Okay? When we start talking about set notation, interval notation, you guys remember interval notation last year? Phrases like that? You ever hear the words? Not necessarily what it is, but what the words are? Okay, no? We will talk about how we write what I just wrote up there in that, what we call set builder notation there. But there's, like on a test or quiz, if you write X can be, and in English, X can be all real numbers except for 1 and negative 1, I would give you credit for that. But I also want, because this is something that I've noticed when I went to school, is that my teachers were lenient with that. Okay, my Algebra 2 teacher was kind of a stickler on it. But for the most part, my teachers were lenient. As long as you could tell me what the answers were or were not in words, it was fine. But when I got to college and I was in a calculus course, and my teacher or my instructor in my calculus course had like 4 degrees from Purdue, and he was like aeronautics, like one of his things was like he was going to be an astronaut or something. This dude was a genius. He knew like 7 languages. He wrote stuff like that because to him that was as basic as you could be. And if I didn't know what that meant, because that was difficult or not basic to me, then I was lost, right? So you're going to get in the situations where you have professors that write it one way, and if you were never exposed to that, you might have absolutely no idea what they're talking about. But if you can read that and interpret, well, that means the exact same thing my answers do, I think it sets you up for success a little bit better. Okay, that makes sense? You good? if you were to graph those, because it says my answers are all real numbers, if you graph those two things, graph the left-hand side and a y1, graph the right-hand side and y2, they're going to be the same graph, okay? But when I evaluate at 1 or -1, it's going to give me a problem. It's actually going to come back as, if we use GeoGebra, it'll come back as an infinite value. Okay, and that's not a number, right? No, there's no gaps here. There are asymptotes. So if we take a peek at it, algebra. All right, so this is the, so those are the two left and right hand sides, right? Okay, and you're seeing that they're overlapping each other. What I did initially was I graphed, I asked this thing to evaluate at 2. So I asked it to plug in 2 right here and see what it gave me back, and it gave me back 2/3. So I plotted 2, 2/3, and you see it's a point on here, right? Okay. Well, if I ask this thing, I'll delete these other numbers up here. If I ask this thing to evaluate at f something really close to 1, so I'm going to go 1.001, okay? And I hit enter, and it gives me that number right there, right? So now let's go, so that's a pretty big number. But if I go f of 1.00001, that's much bigger, right? If I go f of 1.0000001, it's much bigger, right? So what is that one number getting closer and closer to? This number is not getting closer to infinity. That number is getting closer and closer to 1, right? And then this number is getting closer and closer to infinity, right? Well, when I evaluate at f of 1, GeoGebra understands this concept, or is programmed this way. When I go evaluate at f of 1, I do indeed get infinity back, okay? But infinity is not a number. It's an idea. Does that make sense? Because if it was a number, you could tell me what it was, right? And if you could tell me what it was, I can add 1 to it and get a new infinity, contradicting what you thought to be infinity, right? Okay. So that's the reason why 1 is not a solution. We have vertical asymptotes there. Okay. Is that cool? All right, we'll stop there. Tomorrow, go ahead and make sure that you have the second section of notes printed off. We'll start there. That's quadratics. We'll spend more time on quadratics than we did this stuff. Now, it may seem like we spent 3 days on this stuff, but remember those days last week were all wonky.